Welcome to the quantum universe, a world that challenges our everyday intuition. This isn't a realm of apples falling from trees or of the sun rising in the east. Oh no, the quantum universe dances to a very different tune. Our journey begins with superposition, a fancy term that simply suggests that a quantum object can exist in multiple states at once. Imagine being both at home and at work at the same time. Sounds impossible, right? Not in the quantum world. This brings us to our next stop, entanglement. Picture this, two particles are entangled, they are like conjoined twins sharing a profound bond. Even if you were to separate them by the width of the universe, a change in one particle would instantaneously reflect in the other. This spooky action at a distance, as Einstein called it, defies our common sense, but is an integral part of the quantum world. Finally, we arrive at wave-particle duality. In our everyday world, something is either a particle or a wave, never both, but quantum objects. They are the ultimate rule breakers. A quantum object can behave like a particle in one experiment and a wave in another. Confusing? Absolutely. But that's the quantum world for you. These three concepts, superposition, entanglement, and wave-particle duality, form the backbone of quantum theories. They challenge our understanding of reality, and yet they have been proven time and again in countless experiments. With these basics in mind, we're ready to dive into the misconceptions that often cloud our understanding of quantum theories. So, buckle up and let's delve deeper into the rabbit hole that is the quantum universe. The quantum world is riddled with misconceptions, some of which have even permeated the scientific community. Today we're going to address these and set the record straight. First up, let's talk about Schrödinger's cat. This thought experiment has been widely misunderstood, with many people believing it suggests a cat can be both alive and dead at the same time. In reality, Schrödinger proposed this experiment to illustrate the absurdity of applying quantum mechanics to everyday objects. It's not about a zombie cat, but rather about the limitations of our understanding of quantum mechanics. Next, we have the observer effect, often confused with the idea that conscious observation can alter reality. This misconception stems from the principle that observing a quantum system can change its state. However, observation in quantum mechanics doesn't necessarily mean a conscious act of looking. It refers to any interaction that extracts information from the system. So no, you can't change reality just by thinking about it. Another common misconception is the idea that quantum mechanics allows for faster-than-light communication. While quantum entanglement does involve correlations that occur instantaneously, it doesn't allow for faster-than-light information transfer. A measurement made on one entangled particle gives immediate information about the other, but the result of the measurement is random and doesn't carry any meaningful information unless compared with the result of the measurement on the other particle, which requires slower-than-light communication. Lastly, we have the myth that quantum mechanics implies that anything can happen at any time. While quantum mechanics does allow for some very strange things, it doesn't mean that the improbable is probable. Yes, there's a non-zero probability that you could tunnel through a wall, but the chances are so astronomically small that you'd have to wait longer than the age of the universe to even have a hope of it happening. Busting these myths, we can now delve deeper into the more intricate aspects of quantum theories. Remember, the quantum realm might be strange, but it's not a free-for-all. It's governed by precise mathematical laws that, while counterintuitive, give us a stunningly accurate description of the world at the smallest scales. Quantum entanglement, a phenomenon as fascinating as it is mysterious. Often depicted in popular culture as a mystical bond between particles, this concept is a cornerstone of quantum theory. But what is it really? Let's debunk some misconceptions and shed light on this intriguing phenomenon. Quantum entanglement is a physical phenomenon that occurs when pairs or groups of particles interact in ways such that the quantum state of each particle cannot be described independently of the state of the others. This means that if you know the state of one particle, you can determine the state of the other, no matter the distance between them. This is a fact, not fiction, but it's not quite as magical as it may sound. One common misconception is that entanglement allows for faster-than-light communication. While it's true that changes to one particle seem to affect its entangled partner instantaneously, this doesn't mean information is being transmitted faster than light. The correlation between particles is established when they are created, not when they are observed. So sorry to disappoint sci-fi fans, but quantum entanglement won't be powering your warp drives or teleportation machines anytime soon. However, quantum entanglement does have practical applications, particularly in the emerging field of quantum computing and quantum cryptography. In quantum computing, entanglement can be used to link qubits, the quantum version of classical bits, to perform complex calculations at speeds that are currently unimaginable with traditional computers. In quantum cryptography, it can be used to create secure communication channels that are immune to eavesdropping. In closing, quantum entanglement is a fascinating yet misunderstood phenomenon. It's not a mystical force or a means of faster-than-light communication, but a fundamental aspect of the quantum world with real-world applications. With a clear understanding of quantum entanglement, we're ready to explore the intriguing concept of parallel realities. Imagine a world where every decision branches off into a new reality. Welcome to the many worlds interpretation. This theory, rooted in quantum mechanics, posits an almost inconceivable scenario: multiple parallel. Welcome to the quantum realities, all existing simultaneously. The many worlds interpretation is based on the concept of wave function collapse, a fundamental process in quantum mechanics. In the classic view, when a quantum system is observed, it collapses from a superposition of states to a single state. But according to the many worlds interpretation, rather than collapsing, the universe splits, creating separate realities for each possible outcome. Now, let's address the elephant in the room. No, this doesn't mean there's a universe where you're a billionaire, or a superhero, or a rock star. The theory only applies to quantum systems and their superpositions, not to macroscopic events or day-to-day decisions. While it might sound like something out of a science fiction novel, the many worlds interpretation is not just a fanciful idea, it's a serious proposal by physicists. And it's consistent with the mathematical formalism of quantum mechanics. However, it's also not universally accepted. Some scientists argue that it's untestable and therefore not a valid scientific theory. The implications of the many worlds interpretation are profound. If true, it fundamentally changes our understanding of reality and the nature of the universe. But it also raises deep philosophical questions. What does it mean for our concept of identity, of self? If there are countless versions of us, each in their own universe, then who are we, really? From the multiverse, we now turn our attention to the future of technology, quantum computing. Quantum computing, a buzzword that's taken the tech world by storm. But what's the reality behind the hype? Let's explore. Quantum computing is not just another trend, but a promising technology that could potentially revolutionize the world of computing. It's based on the principles of quantum mechanics, using quantum bits, or qubits, instead of the classical binary bits. While a classical bit can be either a 0 or a 1, a qubit can be both at the same time thanks to the concept of superposition. This allows quantum computers to process a massive number of possibilities all at once. However, it's crucial to separate the hype from the reality. While quantum computing holds immense potential, it's still in its early stages of development. The technology faces significant challenges, from maintaining qubit stability to dealing with quantum decoherence. It's not about to replace classical computers anytime soon. And then there's the exaggerated claim that quantum computers could crack all encryption codes, posing a threat to internet security. While it's true that quantum computers could theoretically break certain types of encryption, we're still decades away from such a reality. Moreover, the cryptography community is already developing quantum-resistant algorithms to counter this potential threat. Despite these challenges, quantum computing could bring about groundbreaking changes, particularly in fields where complex computations are required. Areas like drug discovery, climate modeling, financial modeling, and even artificial intelligence could greatly benefit from the processing power of quantum computers. But remember, it's not about quantum computers rendering classical computers obsolete. Instead, they're likely to coexist, each serving their unique purposes. Quantum computers would handle complex, computationally intensive tasks, while classical computers would continue to perform everyday tasks. As we decode the hype around quantum computing, we conclude our journey through the quantum realm. It's a world full of possibilities and challenges, a world that's as fascinating as it is complex. And as we continue to explore this realm, who knows what other mysteries we might unravel. Our exploration of the quantum realm has been a journey through myths, misconceptions, and realities. We've set a solid foundation with the basics of quantum theories, dissecting complex concepts like superposition, entanglement, and wave-particle duality. We've addressed common misconceptions, shedding light on the misinterpretations surrounding Schrödinger's cat experiment and the observer effect. Exploring quantum entanglement, we've separated the facts from the fiction, revealing the real potential and applications of this fascinating aspect of quantum theory. We've delved into the many worlds interpretation, discussing the scientific basis for this theory and its implications. And finally, we've looked beyond the hype of quantum computing, discussing its real potential and impact on the future of technology. The quantum world is a complex and exciting realm, full of mystery and intrigue. But remember, this is just the beginning of our journey. Stay curious, keep questioning, and join us next time as we unravel more mysteries on Yielda.